Uh, it's a very good opportunity for me to share some of our works here. Uh, so our work I'm going to talk about today is about granular fluid flows. It's one type of multi-phase flow, right? And as Shibor just mentioned, um, we focus on particles. So because particles uh, uni can be widely found in industries and niches. So in this area, there are actually many models, but when the particles become dense, very dense, the current models can meet some challenges. So we propose a new model framework by coupling CFD and FEM for this kind of multi-phase flow. So another keyword is large scale because we use FEM to model the particles. So it's a continuum model. Not we are not modeling the particles one by one like DM. So using the continuum models for the particles, um, the method can be computationally more efficient. So that's some work we have done in our group by me under the supervision of Professor Bin Yu and recently other PhD students have joined this project. For example, Dr. Yinghui Wu and Dr. Yang, who have also done a lot of jobs. Okay, this is the outline of my presentation. So I think Shibo have given very good introduction about the particles. So particles, uh, over 70% of industry products actually exist as bulk solids, and in the Earth, uh, particles like sand are the second most uh, matters after the water. So I think I don't need to introduce more about the particles. So here's the problem. So particles have can behave very differently under different load conditions. For example, it can be very dilute, like a gas, and it can like a fluid, which we call dense flows. And in some cases, it is cold static, so the particle doesn't move, and it can keep still. So for currently, if we want to develop some continuum models, there are different series. For example, for the dilute flow, we have kinetic series. For the dense flow, we have visoplastic model or some rheology, granular rheology model. And for the quadratic states, like soils and sand, um, basically we use elastoplastic models. So we can see we have different models, and the different model framework are quite different. So, but the problem is in industries, in many cases, the different states coexist simultaneously. So what we try to do in this work, we try to unify the models for the dense flow and the quasi-static flow because this is a challenge for the current TFM models. So here, uh, uh, I like to mention two popular methods. First is the discrete method, CFD-DM. This method, as we all know, is has a high uh, fidelity, and because it track every particles, but it is computationally very expensive. The contingent models for the particle fluid flow is two fluid model TFM, which uh, can be found in the commercial software like ANSYS. So it's computationally efficient, and it works in a lot of situations, but when it comes to the quasi-static or very dense flow, the TFM often fails. I think this is a well-known challenge, and the inherent reason is the TFM use the kinetic theory or kinetic theory enhanced by the friction stress model to describe the particles. Sorry. So, but if it becomes quasi-static, that kind of model is uh, not that accurate. So, so our idea, this is the overall idea of our job or project. We actually want to replace the kinetic theory by the elastoplastic theory. So because you elastoplastic theory, we can well describe the quasi-static and the dense flows. So but to for this purpose, we need a new method. We cannot use the CFD because the CFD cannot implement the elastoplastic theory. So we actually need to use the uh, FEM, finite element method. But ordinary in traditionally soil mechanics, we use Lagrange FEM, but that ordinary FEM does not work for us because, as I will show later, it often encounters some mesh distortion problem. So here we choose a new FEM method, Euler FEM. So as shown in this figure, in this Euler FM, the mesh does not change with time. It's fixed, like in CFD. And the elastoplastic solids will move through these meshes like some fluids. And by doing so, we can, because CFD is based on Euler coordinates, and the particle phase, for the particle phase, we also use Euler coordinates. So it's easier for us to couple the two methods. And of course, because we all both FEM and CFD are continuous boost method, they can be computationally efficient. And we use FEM, Euler FEM for the particle phase, and the CFD for the gas phase or the fluid phase. And then what we do in this project, we couple them. And this will formulate a new model framework for the multi-phase particle fluid flows. So that's our idea. So we hope that this idea will provide a new model framework for the dense, very dense, or even quasi-static particle fluid systems. So in this talk, I will introduce our method step by step. First, I will introduce how we model the particle flow using the Euler FEM, and then I will uh, introduce how we couple the Euler FEM and CFD to create a new multi-phase flow code. And then I will introduce our validations. So here, why Euler FEM? And I said, if we try to use elastoplastic theory for the particle phase, we cannot use CFD anymore. We need to use FEM. But as shown in the left figure, the ordinary FEM, like that in soil mechanics, the when the soils or the particles moves, the mesh get distorted, as shown here. So this is not a problem if the mesh quality is still good, but eventually the mesh quality downgrade and finally will affect the results. For example, this is the hopper, and we monitor the discharge rate from the outlet of the hopper. We can see if we use Lagrange FEM, the flow rates, eh, the particle it gradually the particle flow will cease, cannot flow anymore. But if we use the Olering FEM, we can indeed get a steady discharge flow rate. That's like the principle of hourglass. So the discharge rate of the particles from a small outlet will finally reach a steady discharge rate. So that's why we use the Olering FEM. So here is the outline of the Olering FEM method. Um, oh, sorry, I need to mention another thing. Uh, s- so Olering FEM is probably still uh, a new words, but people may be more familiar with another term, arbitrary Lagrange Olering method. This is a group method used to in computational mechanics to overcome the mesh distortion problem. So Olering FEM is one kind of this ALE method to overcome the mesh distortion. So that's the governing equation for the Olering FEM. Because it is in Olering coordinates, we will get the convection term. And in this method, the density is a variable. So this is the compressible governing equation. And we have the body force in the momentum equation. And but different from CFD, here the stress sigma, the calculation of this stress is different. Uh, because in SFD, normally the stress will be composed by a pressure term and then a viscous stress term. And but in this model, we use a viscoelastic model to calculate the stress sigma. So basically, if the the deformation is small, all the stress is the shear stress is small, so does not is not enough to drive the particle to flow, which we call is the elastic regime. Uh, the stress will be calculated using a elastic law. And when the particles start to move, which we call uh, that the plastic deformation occurs, we'll use the second line to calculate the stress. So so basically, in this model, two components are very important. First, the elastic law, and secondly, the plastic yield criteria. Yes, and that's the model framework. In our group, in our project, we actually uh, improved the elastic law and the plastic criteria to in order to capture some more sophisticated phenomena. So, for example, here, uh, we that's the theoretical challenge in granular physics. So, this figure is taken from a very pioneering work by Job and Polkin. So, basically, what does this figure mean? So, it basically means that the solid-like behavior and the fluid-like behavior, uh, that transition between the two granular states is more complex than we used to thought. So here, the dashed line is the transition line. We can see first it is smooth. This is a smooth transition. So previously, we normally think that uh, that the friction law is very a sudden change. So below that friction line, it's it's static, solid-like, and above that friction law is the flow. But here, uh, if we look more carefully, that transition is more complex than that. So the transition is smooth, and also it depends on the particle size, or at least there is a length scale in the state transition. And also there's some hysteresis phenomena. So, so that means when the solid state, the transition from the solid state to the fluid state is different from vice versa, right? Different from the transition from fluid back to the solid. So that's some more sophisticated behaviors in granular physics. So we did some work, theoretical work to address that challenge. I will not give details because today we are going to give an overview of our method. So I just mentioned we developed a new frictional law. This friction law all compo include the friction and dialecticity and also interlocking cohesion. Because we can see from this figure, figure D, uh, for so microscopically the particles are there are many cages, right, formed by the particles. So when the particles need to move, they need to go up for some distance. So previously we knew this and we use the dialecticity to the variable dialecticity to quantify this behavior. And in our research, we found that we still need another term, which is called interlock cohesion. This interlock cohesion scaled with the particle diameter, the particle density, and also it should depend on the particle shapes. So anyway, we introduced this a new friction law. So that's the other results. This is the inclined shoot. This is a very traditional configuration to test the granular model. As we can see here, we can reproduce the transition between the solid-like behavior and the fluid-like behavior. And also, when we further increase the inclination angle of this shoot, the flow will become steady. And we measured the velocity field and compared that with the, the experiment done by the Joub in 2006. And we can see that they can agree with each other. So not just test the model in the in-class shoot, we actually test it in many different uh, granular flow configurations. For example, sandpile, hopper, routine drum, and blast furnace. There I will not talk about that in more details. So if you're interested in that, you can read some papers. So then we will move to the main subject of this presentation, how we couple CFD and FEM to generate a multi-phase flow code. So here is the overview of the CFD-FEM coupling. Actually, this is a very, let's say, ordinary method for the coupling because many multi-phase flow use that kind of a method to couple two methods. Basically, we write a passing code to connect the FEM and CFD. Uh, Basically, we have two servers. One is and the two servers are separate. So we use a Python code to coordinate the two servers. So first the FEM starts, and the FEM start to calculate the granular flow, and we then retrieve the velocity results and solid volume friction from the FEM results, and then also, we got the velocity from the CFD, and then we calculate the drag force, and then we apply the drag force and the body force to the granular phase and the gas phase. So there is no significant challenge here. This is mostly a technique development. But one thing I have to mention is the solid volume friction. Because uh, as I demonstrated previously, the FEM are mainly used for the dense flows. So, but in multi-phase flows, sometime or from time to time, the particle phase will become dilute because of the gas, the drag force from the gas. So, how can we let the FEM become dilute and then get a reasonable results of the solid volume fraction? That's actually a challenge in our project. Oh, so here, how can we make the granular gas become dilute? If we can look back to the viscoelastoplastic model. So as I mentioned, it have two uh, components: the elastic law and the plastic law. So the plastic deformation is often volume conservative. So if uh, let's imagine the deformation of some soils. So when the soils moves, the overall volume does not change. This is kind of a constraint imposed by the plastic model. So if we don't consider the dialecticity, the plastic model does not incur some volume expansion or contraction. So in plastic deformation, the volume does not change. That means we cannot the solid volume fraction does not change. But in in the elastic law, of course, it if you consider elasticity, the volume can change, but previously we mostly used the linear elasticity. The linear elasticity is too strong. That means that it's not easy for the bulk granular material to expand its volume or contract. So if we look the the model used in TFM, in TFM, uh, yeah, equation EUS, equation of state is often used. In that equation, the stress increase very rapidly when the particle are dense, but if it become dilute, the stress decrease very rapidly. So that also means if we use the elastic law to describe the deformation of the particles, the elastic modulus E should also be nonlinear, especially when it approaches the dilute state. So that's the idea. Um, to get a law for the elastic modulus, we actually apply the local average method. So we use DM to model a hopper, and we use the average method to get the solid volume fraction and also the pressure. So that's the results. And based on the results, we can get a nonlinear model for the elastic modulus E. So basically, when the solid volume friction is larger than uh, some values near zero point 0.5, the elastic modulus is very large. So the definition is small. But if it lower than zero point 0.5, uh, the elastic modulus reduced to a very small value. That means it can expand its volume. So, okay, that's a summary of the CFD-FEM method. That's the governing equation for the gas phase and granular phase. Uh, so here, as I mentioned in the FEM, the bulk density is, is a variable, it's compressible. So we get the bulk density and divided by the original particle density, we can get the solid volume friction. And we assume that the volume friction of solid and the volume friction of the gas equal to 1. So then we can get uh, epsilon g and epsilon s. And we can use that variables together with the velocities to calculate the drag forces. And on the left are the models for the constitutive models for the granular phase. That's the elastoplastic model framework. And then we introduce the mu aerology. And again, we use the elastic E epsilon S as the nonlinear elastic law. That's an overview of whole model. Finally, I introduced several validation cases. First one is the packed bed. Packed bed is very simple. So we inject the gas from the bottom uniformly, and then we measure the pressure drop, and then we can get the uh, relationship between the pressure drop and the velocity under different cases, for example, different particle diameters, different initial solid volume fractions, and different filling levels. We can see that the pressure drop uh, increased as it should be. So that means we actually implement the drag force correctly in your code. Secondly, we model a spotted bed. Here is the animation with the bubble generated by injecting some gases into the granular particle bed. So, and then we compared the bubble size uh, with the experiment. And of course, if we use different drag force models and different parameters, the results can change somewhat. But overall, we can say that it also agree reasonably with the experiment. So, of course, the current TFM can model the bubble, the spotted bed, no problem. And so, but we use this example to demonstrate that all method can also model this configuration. And again, if we further increase uh, the eject gas, the it will become the fluidized bed. We actually want to reproduce the fluidized bed in a project, but up to now we are not able to do that. This is a very uh, interesting question. On one hand, we think there should be no problem because if we can generate one bubble, we can generate more and more bubbles. There should be no problem. But in reality, we do encounter with some numerical uh, collapse during the simulation. So we are not sure if it is a theoretical challenge or a numerical challenge. So anyway, we cannot reproduce the fluid data bed. So that's a limitation of the current CFD-FEM as compared to the TFM. We know that TFM have no problem to reproduce the fluid data bed. But on the other hand, our CFD-FEM have some advantages as compared to the TFM. For example, here is a collapse of particle bed. This is in the presence of the fluid phase. This is like this situation, like some landslides under the seawater, right? And we can see if we use TFM, as shown by the figure C, the profile of this particle bed is not that accurate. But if we use CFD-FEM, then we'll get a very good uh, profile of this particle bed. So that means if the if the particle become dense or uh, the gas phase is not that strong, the particle phase dominate the whole system. In that case, I think the new CFD-FEM approach will outperform the traditional TFM. The last case is about a cohesive particles flow in a hopper. So this is a classical problem. So if the particles are sufficiently cohesive and the outlet of this hopper is sufficiently small, the particle flow will stop. And because the particle will form a very stable arc above this outlet. So this is a very cohesive and dense problem, which can occur in many situations. Uh, Up to now, I haven't seen any continuum models can simulate this uh, phenomena. Here we use the CFD-FEM. We can simulate the whole process of the arch formation. And showing the figure on the right figure, the small, we can see the small area near the outlet, that's the arc. And we compare our results with uh, this theory. This is the theory used in the design of hoppers. We compare we can see is most all results can basically agree with this correlation. So that means the CFD-FEM results are reasonable, and it could have more potential to handle the highly cohesive particles uh, without with or without the fluids, right? Finally, I'll give a very short message about our work. Basically, we developed the CFD-FEM approach for the dense particle fluid system. So we use the CFD for the gas phase and the Ullern-FEM for the solid phase. So a core innovation of this new method, it unifies the quadratic and the dense fluid states with a continuum framework. But it also has some limitations as I just mentioned. This method is still under development. Um, the scope of the application is not sure. We still need to exploit. For example, the fluid at the bed I just mentioned. we are not sure if this method can be used for fluidized bed or not. We still need more work to explore that. Okay, that's all for my presentation. Thank you for listening.
Yes, yes, very good. Yeah, you give us another different story. Yeah, compared to
Yeah,
Professor Kwan, actually, you like to more details of your research.
yeah,
Okay,
yeah.
and I'd like to show you some questions. First, I'd like to give you the question from Professor Kwan. His question is that particles become dilute due to particle-particle and particle-wall interactions and particle-flow interactions. In the CFD and FEM model, the dilute condition are obtained from particle-to-particle particle-wall interactions. And he means that understanding it correct? Yeah,
Okay. So I'm reading the question of Shibo. Sorry.
yeah. You just because you know there are several questions. I like to show you a question from Shibo. Yeah.
Yeah, yeah, yeah. Sorry. I need some time to read the question. Mm.
It means that it means that the safety and the FD and FEM model, the dilute conditions, is from the particle-particle and particle-wall interactions, or do you consider this as the conditions between particle-particle and particle-wall?
We consider the dilution. I think the broad question is why the particle become dilute.
Yeah, yeah,
Yeah. Uh, Basically, it become dilute because of change of the load conditions. The load condition includes the drag force or the gravity or some boundary forces. So if the external force allow the particles to become dilute, then it will become dilute naturally in our model. Uh,
So you mean the dilute actually is not only by the particle wall, but also come from the local fluid, for example, the turbulence. Yes, due to this,
yeah,
the
yeah.
local flow is very complex. It may be depending on this local flow and the drag force from flow and cause particles, change the stance conditions. Yeah,
Yeah. So imagine if we consider the safety DM simulation. So why the particle become dilute?
yeah,
It- of course, it's because of some forces, right? Some forces drive the particle to move in different ways,
yeah.
and then it will become dilute. So similarly, in our method, um, if there are no external forces, the particle will pack under gravity, right? Then if there are some forces like drag forces flowing this way and flowing that way, that will drive the material to flow in different ways, then it will become dilute.
Okay. And
Yeah.
Shibo's second question is binary conditions play an important role. Can the Zen model can consider this phenomenon?
Uh, binary binary collisions. Firstly, our model is a continuum model,
Mm.
so it's not consider and actually consider the collision with two particles or three particles. I think Shibo's question uh, is about the very dilute situations. Shibo, are you there? Can you further
Yes,
clarify?
yes, yes. I just say in the transition region between dilute and dense,
Yeah,
then probably particle contact not lasting, and it mainly binary.
yeah.
So I'm not sure, like now in your FEM model, you can handle the condition where particle collision are mainly binary.
Mainly binary, because this the two that's different skills, right? Because we focus on continuum skill. Mm. In our continuum models, when the particle become dilute, the overall stress, inner stress between the particles will decrease.
Yeah, that's right.
Yeah, that's I think that's all. That's all for in the continuum model.
Okay.
Yeah, of course, in these DM models, um, there are many more sophisticated mechanisms. But when if we try to build a continuum model, we have to ignore some macroscopic dynamics. Yeah.
Yeah, that's even for the porosity calculation. So in your modeling, you
Yeah.
introduce a certain of like almost like you are trying to control particle interaction to get different porosity. So that's the reason I'm asking if in a under condition, particle collision play an important role to determine particle concentration. Now,
Mm.
in your model, you try to control the porosity calculation by controlling particle interaction. It seems there maybe there's something needed to
Yeah,
uh,
yeah, yeah. I
say.
think your question is mainly about the logic, right?
Yeah,
Uh,
yeah, that's right. That's just the logic. Yeah, that's
yeah. So we actually we do not control the interaction. We control the stiffness, the material property, like all material parameters. For example, the elastic modulus. We make the elastic modulus smaller. It, if the smaller modulus does not mean we have a bigger, have a smaller solid volume fraction, because it also depends on the loads, on the external actions.
so that means when you change the property, so
Yeah.
when you change the particle property, that means the particle uh, interaction become more or less intense than the distance between particles become different. So is the key idea for this porosity calculation?
Mm. Sorry, I need to think about that question. I think
Yeah, you
I need
say
to.
now in
Yeah.
your porosity calculation, you
Yeah.
change the property, right? Particle property.
Yeah.
And then
Yeah.
that means you change the intensity, interaction intensity or collision intensity. And
Uh,
then you can change the distance between particles or the gap between particles or the principle is others.
let's see. I changed E, right? The elastic
Yeah,
modulus. It's like I changed the restitution coefficient of particles.
yeah, that's
That
right. Yeah, that's right.
both are material properties. So
Yeah, that's
if
right.
the elastic modulus is larger, we
Yeah,
cannot allow the material to expand. And similarly, if we make the restitution coefficient with the particle equal to zero, the there will be, you know, the particle will stick together, because they will stick together after clear, right?
yeah, 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 yeah.
So I did not directly modify the force. I
Yeah, I mean, yeah,
modify.
I know, I understand that. Yeah,
Yeah,
but yeah, I just figure out how you can. I mean, how your prosody calculation can be physically meaningful. That's what I'm thinking about it.
I cannot you can you see my slides?
Yeah.
So here, this line is used in TFM,
Yeah.
or similar lines is used in TFM. So basically, you all know that that's the physical meaning of these lines. So if this line can be used as the equation of states in CFD, so
Yeah.
it can become dilute or dense and the different loads force. Similarly, we use this line. We use this line in FEM.
Okay.
Actually, it's quite similar. So that's the physics. So if it's very dense, for example, on this line, it can sustain very large pressure because the elastic modulus is high. But if it become dilute, it can only sustain very small pressure. It's similar. It's similar to this line. Yeah, basically, I think in this regard, the relationship we used is basically equivalent to the model in TFM.
Yeah. Maybe we can have more discussion about the detail after this meeting.
Yeah.
Yeah, you're right. Very complex. Yeah. Okay. I'll give you another question because outside of another platform, the people give you the question. It's very good question actually. For large scale dense particle flow simulations, for example, a system containing millions of particles, what parallel computing strategies such as Stallman decomposition or particle grouping, parallelization, does the coupling method employ used? And how does the parallel efficiency decay with the increase of the computing scale? Yeah. This is another very detailed question here
Yeah.
about communication. Yeah, this is very important.
Yeah. For now, we do not use the parallel uh, parallel computational strategy. And I think we can try that in the future. And because as I show in this presentation, all development is mainly in the theoretical model. So we actually utilize some existing softwares, for example, AUX and OpenFOAM. So as far as I know, both the two software can use parallel computation. And so in the future, we'll try that. So that means we can use that multi-CPUs, but we did not do that currently.
No problem. I'm thinking your method actually is also very useful for the parallel conditions. Yeah, parallel simulations, depending on dense region and the dynamic region, how to change it and how to calculate it, and you just also set some parameters or some. I'm thinking just give a level to definition. What is the dense? What is the dilute? And depending on the different this region, and then you can to use different method actually. Yeah, and this is good suggestion. I'm thinking in future you can also do the same way. Yeah. Yeah, and the time actually is very good, and I also have some questions for you actually. Yeah, and
Yeah.
just now the Shibo actually also asked the question about the phase changes, because in your simulation, do you consider the particle size contribution to the dilute or to the dense? Because from your report, I didn't see anything about the particle size, the rule.
Yeah.
Yeah, in your
Yes.
simulation.
Uh, so I will probably go through that. The most important effects of particle size is in the drag force, I think, right? Uh, Here, this is similar to TFM. In our methods, of course, the drag force depends heavily on the particle size, and also in another part in the model, in the constitutive relationship for the granular phase, the friction law also consider the particle size effects. So the question is that enough? Is that enough? We have that this model consider every aspects, every effects of the particle size. I think according to the simulation results and of course or at the understanding the previous literatures on the multi-phase flow modeling, I think it already captures most of the particle size, the effects of the particle size. Uh, you can imagine what's the difference? What's the major difference of of small particles and large particles in the flow, different flow systems?
Okay, so just now Shibo also asked you how about do you consider the particle and the particle walls interactions? I'm thinking due to as the particle and the particle wall interactions, the particle some may be broken or breakage, and the big particle becomes smaller particles. So the particle size actually is changing. So for your method, I'm thinking in the future you can also consider due to this interactions between the particle and particle walls, and then the phase changes from the dense or from the dilute. I'm thinking very interesting. Yes, actually, for, depending on your method. Yeah.
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 Yeah. Be- Because currently we kind of use the average. We average different particle size. We cannot consider the individual particle size in our model. We basically treat uh, a bulk of the particle size and take an average. Yeah, but if the particle size are different and yeah, that could be very interesting and
Okay.
very challenging. Yeah.
Yes, today you and the Shibo give us very good their presentation. Yes, about the simulations, different simulation methods, and the Shibo actually give us very broad ideas, the areas including the flow bed and engineering and some very specific the problems. And also you give us another different methods, yes, coupling the DNS and say and another methods. I'm thinking give us a good ideas. Presently, a lot of research in this part of technologies actually apply this CFD and the simulation methods to study very complex problems. So I'm thinking as today's presentation, you provide a very good ideas for us to learn some good methods and ideas from these complex problems in the futures. And we will, yes, provide your today's presentation stuff to all the peoples in this platform, in these areas, and in our groups, IMTF groups. Thank you very much for your today's presentations. So, and today the time actually is near the end, and thanks again for your attention, and thank a lot of people's attend our the IMTF 37th the meetings, and hopefully we will give you the next the meetings in next month. Thank you very much, and Albert, thank you. Nice to see you.
Thank you, Professor.
Yes, thank
Yeah.
you. Yeah. And Shibo, yes, thank you very much. So today,
Thank you.
and
Thank you.
we finished today's meetings, and we will quickly provide today's PDF, the presentation stuff to you, for reference. If you have any questions, please read email, connect with both speakers in the future. Thank you very much.
Thank you. See you.
Thank you.
So see you next time. Yeah.
Yeah.